Hello! In this video, we will cover autonomous equations and population dynamics. Okay, so differential equations that have the following form dy dt equals f of y are called autonomous equations. The fact that the independent variable t is not included in the function, the effect that that has is that makes it so that when you go through and graph the differential equation, the graph looks the same as you go horizontally across. I will show you that in just a moment. Okay, so we will revisit that in just a moment. So the one application of autonomous equations is population, modeling populations. And so we are going to spend this video going through and going over a variety of different types of autonomous equations using populations as the setting. Okay, so with that in mind, let's just go ahead and immediately get started by looking at a population system that we could go through and model, and it's one that we've actually done before. It's the base exponential growth model. So in that model, absent other factors, populations will grow at a rate proportional to the current population. So what does that look like? Again, we've modeled this before. dy dt equals r times y. And so in this case, r is called the growth rate. And it just says if you take the current population, multiply by the growth rate, you'll get the amount of new population. Dy dt is the change in y. If y is the population, this is the change in the population. And we can go through and say that y of 0 is equal to y naught. So we can have our initial condition. And if you go through, and again, we've done this, if you solve this, you can solve it by separating it. We get y naught e to the rt. Okay, and we could go through and maybe sketch some pictures for y equals y naught e to the rt. And I can go through and explain the way in which autonomous equations look. So if let's just pick some starting spot, and we'll go through and just draw an exponential curve that goes through there. And so in this case, if we're using 0 to determine where y naught is, then this point would be y naught. However, y naught, of course, could vary. Instead of this being y naught, we could have the value down here. This could be y naught instead. And if you were to go through and draw the curve, and again, it has to model this, it has to fit this, then one aspect of the curve is if you draw it properly, which is maybe difficult to do, but if you draw it properly, it should look the same as you shift across the y value. Okay. And the idea there, that might seem a little odd, but the idea there is that if we were to say pick an actual value here and say this is we're modeling mice growth, and we were to go through and say this is where you have 1,000 mice. If you start with 1,000 mice, then you'd have the population grow. And let's say this is 200 mice. The idea is that when you get to 1,000 mice, it behaves exactly the same as if you started with 1,000 mice. And if you think about that, that does make sense. Okay, so if you have at time 0, you have 1,000 mice and it grows. Meanwhile, at time 0, you have 200 mice and then it takes some time to get up to 1,000. Well, once it does get up to 1,000, at that point, it acts exactly like it did if it started with 1,000. And so that's the idea. That's the graphical behavior for autonomous equations, is that they always look the same if you go across horizontally for the y value. And you could even, add another case up here or something like that. You can say, oh, well, what happens if we start with 10,000 mice and then you draw, a curve there, and then this curve here should look the same as this curve here, should look the same as this curve here. It's just a shifted version of that curve. And so that's the way that autonomous equations work. And the example that we can give with populations really fits that example well. So if you have 10,000 mice initially, or if you grow to 10,000 mice starting at 1,000, or if you grow to 10,000 mice starting at 200, in either case, once you're at 1,000 mice, then the system behaves the same. Okay, and so that's the simplest population growth system, is just base exponential growth. And you can see just visually what that looks like. It just looks like an exponential curve. All right, so let's go through and introduce something to make the model more complicated. We can introduce a limiting condition or a limiting factor of some kind. Examples of limiting factors could be space or food. So something that just prevents the population from continuing to grow, without limitation. Okay. When that happens, we call the name for that model is the logistic growth model. And the way that ends up looking as a differential equation, at least this is the way that we're going to introduce it, is it would look like this. Okay, so before we had R here as the growth rate, and that never changed no matter what the population was. And what we do to model logistic growth is we put in an H of Y and we say, so this is the growth rate now, and the growth rate is going to vary with the population. So if the population is small and not near the restricted space or or running out of food, then the population grows in an exponential type fashion. However, as the population approaches the limiting factor, whether it's space or food or some other condition, then when that happens, the growth needs to level off and stop. Okay, and so that's the idea: is we can go through and start at this point, and what we're going to do is we're going to figure out, well, what should H of Y look like if it meets that description. So, what were the characteristics that I just named? Right. So, what characteristics would H of Y have? Okay. Well, what we want is we want H of Y to be approximately R when Y is small. Right? When we're not near the restricted food or space, we want to have this behave like the previous model. We want it to behave like R times Y. So we want H of Y to be approximately R when Y is small. And then we want H of Y to decrease as we approach the limiting condition. And then finally, if we're above the limiting condition, right? So if we have a population that is bigger than the amount of space or food that can support it, then we want the growth to be negative. We want to actually have a negative growth rate. Okay, and if you play around with this, we can come up with a function, the function H of Y that models all of this. Maybe we should say an H of Y, not the, because maybe there could be more than one. An H of Y that models this is H of Y equal R minus AY. So let's just spend a moment and examine that. Does it work? Right? So if if Y is small, if you plug in a small value, a small population, what happens, right? So if Y is small, then you're going to get a small quantity for A times Y. And so R is going to be the dominant factor when you do that. And then as Y gets larger and larger, the fact that you're taking you have a negative coefficient here, it's going to make this quantity, this negative quantity, get larger and larger. Eventually, it will approach zero, right, as we approach the limiting factor. More on that in a moment. It's kind of hard to see the limiting factor in here. The way that it's written, the limiting factor is not clear, but we'll make that clear in just a moment. But if this gets bigger, then you could see that you're going to have a negative value here, and it's going to counteract the R value. And then eventually, once y gets large enough, this negative value will become larger than R, and you'll actually get a negative h of y. So it does do what we would like. If we take that and just plug it into our formula, we get dy dt equals r minus ay times y. And this formula here is called the Verhulst or the logistic growth model for populations. The model that can be rewritten if you go through and factor out the R. And once you factor out the R, then it also becomes clear to see the limiting condition in here. If you pull out the R, what happens? Well, if we factor out the R from R, we get 1. And if we factor out the R from negative ay, what we can do is we can write that as y over k times y, where k equals R over a. K is the limiting condition, right? Whether it's population or space, it's the size of the population where we're going to start to run into problems. And you can clearly see that if you go through and play around with this piece here, right? Because this became this whole thing, right? So the y just dropped down, and so going through and interpreting this, you could see if you go through and make y larger and larger, right? Then you're going to get this piece here. You're going to have y minus, y. You're going to have 1 minus y, which if it's smaller than k, this quantity is going to be less than 1. So you'll have y minus something that's less than 1, and that's going to get you a fraction, right, that is less than 1. And if you take something that's less than 1 times r, you're going to get a growth rate that is slowly getting smaller. And then as y approaches k, this is going to approach 1. That's going to cause the fraction here that you have that's less than 1 to get closer and closer and closer to 0. As this gets close to 0, it's going to take the growth rate down to 0. So as y approaches k, this is going to approach 0, which is going to cause the growth rate to approach 0. And then if y gets bigger, somehow gets bigger than k, then this will be larger than 1, and then you'll have 1 minus something larger than 1, and you'll have a negative value here that you're then multiplying by r. And so you could see, if you look at this, it's really, really clear that it has all of the characteristics that we just talked about, right? If you have a very small y, then this is going to be very small, and you'll have 1 minus something very small, and then you'll have a large r, and then the other two scenarios that we just discussed. Okay, and so the next thing that you would expect is that we would go through and solve this differential equation the same way that we did the earlier example, the exponential growth model, by separating it. However, we're not going to do that. Now, you could. Now, the nice thing about autonomous equations is that they're always separable. okay, because of the fact that we don't have a t in there. You can always take all the y stuff and divide it over here under the dy, and then move the dt over and always have y's and dt on the opposite side. So you can always go through and separate autonomous equations. And so because of that, assuming you can solve the you can integrate dy over this, you can always go through and solve it. However, we're not going to go through and do that. Instead, what we want to do is we want to go through and see if we can figure out what the solution would look like without having to go through and solve it. And so this is a neat thing that you can do with autonomous equations that we'll make clear as we go through the video. But it's a real neat, interesting kind of thing that you can go through and do. And so let's just see how it works. All right, so what we want to do is we want to try and graph this. So to get us started, what type of information can we go through and pull out of this, okay, without really even doing any major calculations? Well, in an earlier video, one of the things that we went through is we went through and defined was equilibrium solutions. We said equilibrium solutions are where dy dt equals 0. That's where you end up getting a horizontal line across your your solution set. And so it's really easy to go through and find equilibrium solutions when we have an autonomous equation written like this. And so all you've got to do is go through and just take, the right-hand side here and set it equal to 0. Right? So we can find equilibrium solutions really easily. And to do that, you would do r times 1 minus y over k times y equals 0. And if you solve this, you'll get y equals 0 or y equals k. And so these are our equilibrium solutions. Okay, so how can that be used to help us graph? Well, again, you just have to recall the way the equilibrium solutions work, right, is that if we have our, hold on, needs to go the other way. So if this is modeling our region for going through and graphing the differential equation, we're going to have y versus t. And we know that if y is 0, right, if we go back, if y is 0 and you plug it into the differential equation, it's going to make the rate of change dy dt equal to 0, which prevents the graph from changing value. It's just going to stay at 0, right? So if you've got y equals 0 and then dy dt equals 0, the slope equals 0, then that means you're going to end up with a horizontal line. And so that's what we have here. So at 0, you plug that in, the rate of change is 0, and so that means that your solution is also going to stay 0. It can't change values. So let's go through and we can pop in a solution in red. You can't really see it, but you can just kind of move it a little bit, and then you can. Okay, and then the same thing happens at k, right? If you go through and let's just take one more look here. If you plug in k for y, then you're going to get 1 minus 1, which is going to be 0. And so then the rate of change is going to be 0. So if you start at k and then the rate of change is 0, then that means you never leave k. Or if the slope is 0, then you never leave k. You end up with a horizontal line. And so, hold on. And so we know that these two things are going to be solutions to the differential equation. Okay, now the question is, what do the rest of the solutions look like? Is there any way that we could get even more information other than just the equilibrium solutions? So we pulled out the equilibrium solutions by taking our differential equation and setting it equal to 0. That told us where the slopes are 0, which again prevents you from changing the value. It's just you end up with a slope of if the slope is 0, then you end up with a horizontal line. What else? So what else could we do? Well, what we could do is we could go through and again recall that we have dy dt here on the left-hand side. That's a slope. So we're saying we've got the slope equal to this thing. If we knew how this behaved, then that would tell us how the slopes behave for the differential equation, for the solutions of the differential equation. All right, so how could we go through and figure out how this behaves? Well, what we could do off to the side, we'll do it down here below, and then we'll kind of continue to play around with our picture. What we could do is we could graph this. Okay, so what does this look like if we were to go through and graph it? All right. Well, we can see here that it's going to, if you plugged in, right, if we had, if let's, I think we need to be a little bit clear. What do we mean by graph it? So we're going to say this is the y-axis, okay, and then this is the function. We're going to call this f of y. If you go back to the first page in this video, you'll see that we're modeling things where dy dt equals f of y. So we're saying this is always f of y. And so what we're going to do is we're going to have f of y versus y. And yes, that's unusual, right? That's different than what we're accustomed to doing. Normally, normally we do have the function here, but it's normally x versus f of x. Now it's going to be y versus f of y. And it's because our differential equation is in terms of y. And then we're setting the differential equation equal to, and we're calling that f of y a function of y. And so what we're doing here is we're graphing the differential equation y values are being graphed on this axis, right? The solution of the differential equation y is on this axis, and then the derivative is on this axis, right? Because dy dt equals f of y. So that's a little bit confusing. But in this case, what we can see is we could see if we plug in y equals 0, then we get dy dt equals 0. And so the equilibrium solution here ends up being modeled by the point here. And then the equilibrium solution here ends up being modeled by the point here. And that should hopefully kind of make sense because this is the y-axis and this is the y-axis. And yes, one of them is vertical and one of them is horizontal, and that is confusing, right? The difference here is that the horizontal axis in this case is t, and the vertical axis here is f of y, and so they're not the same, right? This one is y versus t, this one is y versus f of y. Okay, as far as why we would do this, we have the y-axis here and the f of y. That will become clearer as we continue. So let's just keep going, and then the why we would do this, and if this is confusing, it will become more useful in a minute, and then hopefully that will help to overcome how confusing it may be to you. And so, all right, so let's just continue. So if you go through and this thing is f of y, let's just rewrite it over here and ditch the dy dt for the moment. All right, so we've got f of y equals r times 1 minus y over k times y. Okay, so if you plug in y equals 0, then f of y is 0. If you plug in y equals k, then f of y is going to be equal to k, or equal to 0 as well. All right, so for an input of 0 and an input of k, you get 0 for your output. Now, in terms of graphing this, all right, so that's what we're trying to do here, is if you go through and multiply this out, right, what do we end up getting? So we're going to have r times 1 times y, so we're going to have y times r, and then we'll have y times negative y over k times y, and then so that's going to be negative y squared over k times r. And the critical thing here about this, and the reason that we're multiplying it out, is this negative, right? So what does that tell us? It tells us that if we were to graph this, right, that since this is a second degree polynomial, that it's going to open downward, right? We're going to have a negative coefficient for a second degree polynomial. So that's going to open downward. And so it's going to tell us that the picture looks like that. Okay. So we've got at 0, we've got k, and we've got this opening downward, right? And so since this is in the form of a parabola, and we've got the intercepts here are symmetric, what does that tell us? It tells us that the center here is at the point k over 2, right? And if you plugged it in, you'd get f of k over 2. Not that that is that important, but that's what you'd get if you went and plugged that in. Okay, and so we get this picture. So we finished graphing it. So what is this? What can this picture tell us? All right. Well, it can tell us some stuff. All right. So it tells us that if we have y less than 0 or y greater than 0, or not greater, sorry, greater than k, y less than 0, this, or y greater than k, this, what happens? If y is less than 0 or y is greater than k, then f of y is less than 0, right? The output that you get for your function is going to be less than 0. Well, what do we know about f of y? What is f of y? Well, I mean, we've been talking about f of y down here, but what did we do? We went through and we took our differential equation and we called the right-hand side f of y. We know that equals dy dt, so that tells us that dy dt is less than 0. Well, what does that tell us? What's the point of that? How does that help in terms of going through and graphing it? Well, if this graph is y versus t, then dy dt is going to be a slope that's on this graph. Okay, and so what this is telling us is it's telling us that the slopes are going to be negative when we have y less than 0 or y greater than k. Did that blow your mind? Okay, so what it tells us is we could go over here on our picture, and down here below 0, which is the equivalent here to the left, okay, what we're going to have is we're going to have negative outputs for our function. So we're going to have negative derivatives. And not only that, but as you go to the left, those negative values are getting larger and larger negative values. So near 0, we have a small negative. And as we move to the left, as we move this way, the outputs are getting larger and larger. And so we have negative slopes that are getting more negative. And so to represent those negative slopes, I'm just drawing a negative slope on here. And then same thing above k, right? It's the kind of the symmetric here. If we're just a smidge over k, we have a small negative value. But as we move, as y goes upward, which is the equivalent of going to the right here, the f of y gets larger and larger negative results. All right, so we're going to start off with a negative slope and get a larger negative as we move upward. Okay, and that's all this that's all that from this picture here. We can all interpret that from this picture. Okay, that's what this curve is showing. It's showing that as you plug in y values that move to the left, you're getting larger and larger negative outputs. Those negative outputs are f of y. F of y is dy dt, so you're getting larger negative slopes. Yeah, so that's how it works. Confusing or not, that's how it works. And then the same thing happens over here. If you go through and you plug in something near k, So you plug in, let's you plug in a value, pick this point here, you go through and you plug that in, then you're going to get this as your output, and then that's going to be your f of y. So your f of y is going to be that value. So it's a small negative. So we've got a small negative if we're near k, but if you move further away and you plug in a y value that's significantly larger than k, then you're going to get a larger negative output way down here. And so we need to have a larger negative slope. And then finally, if we go through what's happening between these two, we have 0 is less than y is less than k for all of those f of y is greater than 0. So we have positive slopes. How can I tell it's greater than 0? Well, from our picture here, right? From our picture, right? So between here and here, no matter what y value you plug in, you're going to get a positive f of y value. And since f of y is the slope, we're going to get positive slopes. Okay, and one more thing about these positive slopes. How do they behave? We can tell by looking at our picture here. How do they behave, those slopes? Okay, well, the largest value occurs right here at k over 2. That's going to be our largest slope. When you plug in k over 2, that's where the largest f of y value is going to be, right? If you plug in k over 2, you get out f of k over 2. So that's the biggest one. Anything else that you plug in is going to give you a smaller value. So if you pick this point here, you're going to end up getting a smaller f of y value there. If you pick this point here, you're going to end up getting a smaller f of y value there. And again, since these are the slopes, we're going to have the max slope at k over 2. So we have max f of y is at y equals k over 2, and that tells us that max slope dy dt is at y equals k over 2. And how do we use that? Well, we can go here to k over 2, and we can actually go through and put in a dashed line to represent the fact that we have the max slope is there. And to go through and represent those slopes, you can just, the way that I did, for our other slopes, I just drew little slopes on here. What we can do is we can draw little slopes on here. So we want a steep one here where we're going to have the max. And then as you move away from k over 2 towards 0, as we move downward, right, those f of y values get smaller. So thus our slopes get smaller until you get to 0. So we want to draw shallower and then a yet shallower. And then if you do the same thing over here, if we're at k over 2 and we're moving toward k, our outputs, our f of y values get smaller, which means that our slopes get smaller, our dy dt's get smaller. And so we can go through and draw, pictures like that. Now, this is all, you'll notice I went through and I drew all these slopes at 0. Why did I draw them at 0? Well, it's because it's an autonomous equation, right? No matter what the y value is, it behaves the same from left to right across the graph. So if we have this slope at this point, we have the same slope here and the same slope here and the same slope here, right? That's the idea that we discussed all the way back at the beginning, right? So if you have 1,000 mice here and you have 1,000 mice here, then it's going to behave the same, right? So the same thing is true in our picture, right? If this is where the 1,000 mice is, if this is the slope at 1,000 mice here, then we're going to have the same slope at 1,000 mice here, even if we started with less. Or here. And so that's the neat thing about autonomous equations, is that if you can figure out what the behavior is, right, for any value, in this case, we're figuring it out where t is 0, then you can just slide that value across the graph and it stays the same, right? And so we could go through and just take other curves that we drew and you can slide those over as well. And what we're doing here, hopefully this seems a little familiar. We're going through and we're generating a direction field. And how can this direction field be used to graph the curve? Well, what we want to do is just draw curves that fit onto these slopes that we've created. Okay, and so the way that you could do that, let's try a different color, is you can just pick a starting point. Let's start here, right, toward the bottom. And what we want to do is we want to just move in this direction until we kind of get close to here, and then at some point we want to change, right? So this is a shallow slope. It's getting steeper, and so at some point we want to make the slope a little steeper. And then when we get you know where this dashed line is, we know that the slope needs to look like this, even if it's not there, right? So we have that same slope here and here and here. And so whenever we get close to that, we just want to make sure that we pass through that dashed line in a slope that looks like that. And so let's just do it. All right. So we're going to have something that looks kind of like this. It's going to go up, and then we want it to be, um, tangent to this. And then as we approach the dashed line, we want it to be tangent to that, right? And then as we get near this region here, it needs to be tangent to that. And so we need to kind of have it start to level off, right? And then as we approach this, we need it to kind of be tangent to that. And you can just kind of continue from there, and we get a curve that looks about like that. Okay. And now, so that's an example potential solution with this as our starting point. Now, what if we started here instead? Okay, well, what we want to do is, as you draw the curve, you want to draw the same shape that we have here, just shift it over, right? So if just do your best with that, right? So it's going to look about like that, right? And you can see that it's the same shape, so again, that's our idea, that with autonomous equations, the graph looks the same as you work your way across from left to right horizontally. And you could do the same thing, starting at this point. So just draw a curve that kind of fits there, and then at this point, and we can go through and generate our curves. And you could do another one here if you wanted. And then below, right? So again, we want to, same idea. We just want to fit this onto the slope. So we want to draw something, maybe look about like that. And then down here like that. And again, if we shift it over, it should land right on top. And then down here, same idea. So you could draw something that looks like that. And then if we started higher up, it should look, well, that one's a little harder to do. Should look about like that. And there you go. And so that's what we've been able to do, is we've gone through and taken the information from our autonomous equation. Okay, we found equilibrium solutions, and then we used the graph here of what the differential equation equals, what dy dt equals, to go through and generate information about what the sign of dy dt would be, for the curve in various regions. Okay, and that enabled us to generate a direction field and then draw potential solutions. And so that's what we're going to do moving forward throughout the rest of the section, is rather than actually go through and solve these, which we could do, they're separable equations, you could go through and solve them. Instead, what we're going to do is we're going to go through and create these graphs of the solutions just by using the equilibrium solutions and using this, the equivalent of this picture, right, for different cases. So what is this called? What was this thing? What did we do here? Well, we graphed dy dt, versus y, and this is called the phase line. Okay, so let's go through and try another one like that, and hopefully that the next one will seem a little more familiar. And will seem a little less confusing with each additional example that you do. All right, so this one is called the critical threshold model. And so we start off. Suppose we took our last model and just put a negative in front of it. Right? If we go back and look, so this has no negative, just has this, that's our model, r times 1 minus y over k times y. We're just throwing in a negative in front. What does that do? How does this change things? Okay, in terms of going through the process that we just did on the last one, what did we do first, right? What did we do first to go through and create this picture? We started off with equilibrium solutions. So you want to go through and find the equilibrium solutions first. To do that, take this, right? So this is f of y. Take f of y and set it equal to 0. So we're going to have negative r 1 minus y over t times y equals 0. And then if you solve it, you're going to get y equals 0 or y equals t. Let's go through and we'll put our picture over here on the right-hand side. So we have at 0 and at t, we have equilibrium solutions. And with equilibrium solutions, what happens? We have these horizontal solutions that just go across. And we end up getting the same value for all t, right? We end up getting, if you start off at t, then dy dt is 0. So you end up with a horizontal slope, which gives you a horizontal line. Right? And then this, just to remind you, this is the t-axis, and this is the y-axis. Okay, so there's our equilibrium solutions. That's step 1. Step 2, we want to look at the phase line. All right, so what is the phase line? It's the graph of f of y. It's the graph of the right-hand side here, which is what's equal to dy dt. So this is going to tell us information about dy dt. And since dy dt is slopes, this is going to tell us information about the slopes. So you can go through and draw a little picture here, and we're going to have f of y on this axis. We're going to have y on this axis. And the way that you can go through, well, there's a couple ways you can do this. You can just take the equilibrium solutions here, since this y-axis and this y-axis are the same. We know that at y equals 0, we end up with a slope of 0, and we know that at y equals t, we end up with a slope of 0. So you can go through and just put 0 and t on your picture. You know that that's going to produce 0 for f of y because of the fact that we know that we have a 0 slope for dy dt. Okay. And then if you go through and take this, right, this is f of y. If you go through and take that and you multiply it out, what is the sign that we're going to have on y squared, right? That determines how the quadratic, that determines how it looks. And it's going to be a positive slope. So we know that the graph is going to look, let's try that again. It's going to look something like this. Okay, that was better. It's very hard to go through and draw a shallow parabola like that with the writing tablet. And then, again, this is a parabola, and we know the parabolas are symmetric. And so if we've got intercept at 0 and t, that tells us that halfway between them at t over 2 is where we would get the lowest value, right? The bottom, the vertex. And if you took that, you could actually plug it in and figure out what that is. And it's going to be f of t over 2. Okay. And then finally, just like on the last picture, or just like on the last graph that we did, we can go through and take this and use it to interpret information about dy dt, our slopes, right? So we can go through and we can say if when y is less than 0 or y is greater than t, right? So less than 0 to the left, greater than t to the right, what can we say about f of y? Well, we can say that it is positive. It's above the y-axis. It's positive. So if y is less than 0 or y is greater than t, then f of y is positive. And again, since this is where I think it gets confusing for many students, is that f of y is the same thing as dy dt, so that tells us that dy dt is positive. And so on our graph, we can go through and we can draw some positive slopes in those two regions. All right, so when y is less than 0, that's this region here, we can go through and we can draw positive slopes this time, not negative slopes, positive slopes. And what can we say about those positive slopes? Are they getting more positive as you go downward? All right, are they getting less positive? So should I start off drawing something that's shallow and positive and then draw steeper positive lines? Or should I do the opposite? Should I go through and start off drawing a very steep positive line and then draw shallower positive lines? Okay, well, the way that you can figure that out is to go through and look at what actually happens. Near 0, if I pick a point here, pick a y value. So if I pick a y value that's near 0 and I plug it in, what type of f of y value do I get out? I get out a small positive value. If I pick a number that's further away from 0, as I go further from 0, what happens if I plug in a value? I end up getting out a larger f of y value. So small value is for y corresponds to a small value for f of y, which is a small slope because f of y is the same as the slope. And if I move further from 0, I get a larger positive f of y, which is going to give me a larger slope. So all of this is a way of saying you're going to have a shallow positive slope and then a steeper positive slope as we move away. And then it's the same thing over here. Near t, we have a shallow positive line, and as we go away from t, you get steeper positive lines. And then between 0 and t, when 0 is less than y is less than t, that's when we have f of y is negative. So, and again, since f of y equals dy dt, that's when dy dt is negative. That's when we're going to have negative slopes. So between here, we're going to have negative slopes. So how could we go through and draw those negative slopes? Should we just draw a bunch of negative slopes in here? No, we want to take it slow here and look to our picture. What can we see about how those negative slopes are organized? Well, the most negative slope, the lowest output for f of y, occurs at t over 2. And so we could say here we have the max negative slope at that point that's halfway between the two. And you can go through and draw the steepest negative slope there. And then as we go towards 0, we get negative values that get smaller. So we're going to have less negative slopes. We're going to have shallower negative slopes. And so you want to go through and draw shallower negative slopes. And then as from t over 2, as we go toward t, we're going to get less. We're going to get negative values, but those negative values are going to get smaller. So we're getting less and less negative slopes on the other, up above as well. And so you want to draw shallower negative slopes. And then once you've done this, this is the equivalent picture that we had here before we went through and created the direction field. So the next step is just to take those and translate them across, because whatever happens at y equals 0, you see the same behavior at y equals 5 or 10. It just shifts across. And so you can go through and draw like that. And then we could draw slopes like this. And then here. and here, and do your best just to make them parallel. And then here, very negative, and then less negative, and less negative, and then positive, and more positive. And from there, you can go through and draw some curves. So we could pick a spot here and do kind of the equivalent to what we did in the last picture. So just start off heading in this direction. So the idea is that whatever we draw, the slopes should fit onto it. All right, so you can go through, and this should be a tangent line to our curve. So we want to start off heading in that direction. And then as we approach this guy, we want to make sure that the shape of our curve is tangent to this, right? Or this would fit onto it as a tangent line. And so we want to go through and draw something like that. And then as we approach this, we want to, same thing. And then as we approach this, same thing. And then as we approach this, same thing. And then you can kind of just finish it up here. Okay, if we start off at this point instead of this point, what you want to do is you want to draw the same basic shape, just shift it over. Okay, so the behavior here is going to be the exact same behavior that we have here that's directly across from it. So it should look kind of like that, right? And so you can see it's if you just shift it across, you end up with the same behavior. And the same thing here, and so on. And then we can go through and draw just something up here that does the exact same stuff, right? Tangent, tangent, and then down below, we can go through and do something like, so like that, and then tangent like that. And we end up going through and being able to generate our picture, which has direction fields and solutions onto it. And at no point did we go through and solve the differential equation. We did not have to go through and plug in a ton of values to generate the direction field. Instead, we used this phase line picture that enabled us to go through and figure out what the direction field would look like. So it's like a shortcut. So the phase line allows us to go through and use it and create a shortcut to generate the direction field. Okay, now as far as what type of situation this would model with population, so the name of it's the critical threshold. So what would this model? How would this model population growth? Okay, well, if you look at it, what's happening here is that if you're below this t-value, then the population declines. And the closer you are to the t-value, the longer it hangs on, right? You can see it kind of hangs on for a while and then collapses. And as you are further down below t-value, the population falls much faster, right? So you get an exponential decline in the population if you're well below t, right? And so if you're above t, the population grows. If you're below t and you're close to it, it hangs on for a while, right? So it kind of hang on for a while before it ends up going downward, right? And then if you're well below t, then the population just dies off, okay? And then ignore these negative values because they don't really make sense. You're not going to have negative populations. And so what would that situation model as far as if you think about a population? Above t, it would grow. Below t, it would die off. Okay, well, what T would model in this case, you could think of it as modeling maybe in the wild, it could model like the concentration of animals in an area. And is that concentration high enough where they can find each other to breed enough to maintain the species? Okay, so a typical example could be like wolves in Yellowstone National Park. You need enough wolves in the park so that they can find each other to end up breeding and creating enough wolves to reproduce and build up the population, maintain the population. So what this is modeling is that if the concentration, if the number of wolves in the park is too low, then there's not enough wolves to find each other and the population dies off. And the closer you are to that, to T here, the closer you are, the more it hangs on. And so that's why they go through and they add, or maybe they're not doing this anymore, but they used to add wolves to Yellowstone to try and build up the population to get it above T. And once it's above T, then the population can just take off and grow exponentially. All right, so this T value is called the critical threshold, right? It is the critical number needed in order to have the population grow. Anything below that, and the population, there's too few to go through and reproduce, and so the population dies off. You could also think of this as like the mice and the owls example, where you needed a certain number of mice in order to reproduce, and even after losing population to the owls, to still have enough to continue to grow the population. Okay, and so that's the critical threshold model, and it's, in a way, it's the opposite, right? So here we have the logistic growth, right? In that case, if the population is below K, then it grows up and it just stops at K. If it's above, then the population dies off and declines to K. And then this is the opposite when we have this critical threshold. If we're above the threshold, we grow, and if below the threshold, we die off. Okay, and so those are the two principal models in terms of population growth. Okay, and then the last thing that we're going to look at is you can combine the two models. All right, and so how do you do that? You just put the two together, really. All right, so we're going to have negative r times 1 minus y over t times 1 minus y over k times y. And so one thing about this is that the critical threshold needs to be less than the limiting value for the population. And so if we start off with this as our model, we can go through and just as a third example, see how to generate the graph. All right, so step one, you want to go through and find equilibrium solutions. To do that, take dy dt, take f of y, right, which is what dy dt equals, and set it equal to 0. So we're going to have negative r times 1 minus y over t times 1 minus y over k times y equals 0. If you do that, you're going to get y equals 0, t, and k. So in terms of our graph, we're going to have equilibrium solutions at 0, t, and k. And we can go through and draw those in red. Okay, and then can we go through and figure out more information about how the populations behave outside of 0, t, and k? Of course we can. We can go through and look at the phase line just like we did previously. So we can go through and draw the phase line. And so we have y, we have f of y. And what do we know about y? Well, we know from this picture that y has equilibrium solutions at 0, t, and k. So it has places where dy dt equals 0 at 0, t, and k. So we're going to have 0, t, and k. Okay, and then the next thing we need to do is to figure out what does the graph look like going through these points. Well, what you can do for this is you can rely upon an old technique from pre-calculus. And so that technique is that if you took all this and you multiplied it all out to generate the leading term, what would the leading term, what would it look like? So we'd have y times y times y times negative r. What's that going to give us? So we've got negative y times negative y, that's positive y squared, times another y, that's y cubed, times negative r, that's going to give us a negative y cubed. So negative y cubed, that tells us that it behaves something like this, right, and like this. So that's the way, that's the negative of y cubed, right? This is a technique that it's called going through and finding end behavior. So you can find the end behavior for this polynomial, and at the extremes, it's going to behave like negative y cubed because that ends up being the leading coefficient or the leading term. And so from there, what you can do is it has to go through these points, and so you can just kind of connect the dots. And we'll just slide this over. And so we know our phase line is going to look like that by using the end behavior, and then it has to go through these points. Oh, and one other detail. Is this the way that it has to go through these points? It is. Again, this is an old pre-calculus technique. You can use the multiplicity that tells you that it passes through each one of these points. Okay. As far as where these are, where the minimum is here, where the maximum is here, you'd have to go through and solve for that. It's not halfway between 0 and t, or halfway between t and k. You'd actually have to go through and solve for it. So how could you do that? Well, you could use a Calc 1 technique, right? So we have f of y, it equals this. So we know that f of y equals negative r times 1 minus y over t times 1 minus y over k times y. This is our graph. We could go through and find f prime of y and then set it equal to 0, and that will generate the places where there's a horizontal slope. So we could generate where that is, and we can generate where that is because we have horizontal slopes there and there. Okay, so we're not actually going to go through and do that. It's a hassle. And so what we're going to do is we're going to say this is y1 and this is y2. We're just going to put points there and say wherever that is, we're going to call that y1 and y2. And if you're interested in this, you can go ahead and take the function here, find the derivative, set it equal to 0, and you can try and solve for what these would be. Okay, what you should end up with is that y1 comma y2 is equal to k plus t plus or minus the square root of k squared minus kt, see, aren't you sorry you asked, plus t squared divided by 3. That's what this value and this value are. So this value for the minus and this value for the plus. Okay, and so on our graph, though, we know that we could go through and put y1 somewhere between these two, y2 somewhere between these two. We could represent them with a dashed line. And what do we know about the behavior at y1? Well, we can see that our function takes on the largest negative value for this interval between 0 and t there. So we're going to have the largest negative slope between 0 and t at y1. And so we can draw the steepest negative slope there. And then between T and K, that's where we have the largest positive slope is at y2. All right, so that's going to be the location where we have the largest positive value for f of y on this interval. And so we have the largest positive slope. All right, and then what's happening here away from y1? Well, the values for f of y become less negative, right, as we approach the y-axis in both directions. So we're going to get shallower negative slopes as we move away from y1. We're going to get shallower negative slopes as we move away from y1. Okay. And how about between t and k? Between at y2, as we move away from y2, we're going to get smaller positive values, and so we're going to get shallower positive slopes. Okay, and then beyond k, what's happening? So f of y is negative and becoming increasingly negative. Like we're getting a larger negative value as you head this way, right? Since this way is equivalent to going upward, where our negative value is going to our negative value for f of y, which is the same as the slope, is going to become a larger and larger negative number. So we start off with a small negative number, and then we get a larger negative number as we work our way upward. And then despite the fact that populations really can't be negative, that doesn't make sense, we can go through and consider the what's happening on the other side of 0 here. We start off with a small positive number, and then as we go this way, the positive number gets larger and larger. So you start off with a small positive slope, and then you get a larger positive slope as you move downward, which is the equivalent of moving leftward in this picture. And so we've got all of that. You can take all of that and slide it over. And if you do that, you'll go through and you'll generate your direction field. And then the last thing that we can do is to go through and graph some solutions on here. So just slide these over. And it's going to take a minute. And then finally, we can go through and draw some curves in here, right? So we could go through and pick a spot, say right here, draw in the curve. So we want to start with a curve that fits where this tangent line would fit onto it. So it's going to look about like that. And then it should level off and level off some more until it looks like that. If you start with something above that, it should start off shallow, becoming more negative, then less, right? And if you do a good job drawing the picture, this piece here, if you shift it over, should land right on top of this piece, okay? And we could pick a point here above. It should curl up, then level off. And if you start here, it should start off upward, level off. Yeah, how about above? And then the negative case, which doesn't really actually make sense. You can't have a negative population. And so in terms of our model here, so here we have our limiting value. Here we have our critical threshold. And of course, here we have no population. The population's died off. All right, and so what happens in this case? So if we're below the threshold, the population goes to 0, dies off. If we're above the threshold, the population grows. until it gets close to the limiting value, like we run out of food or run out of space, and then the population levels off. If we're above the limiting value, then the population dies off until it approaches the limiting value. And so you can see this models all of the different possible situations, right? You start off, Yellowstone has too few wolves, the wolves die off. A few years later, you import a bunch of wolves. This time, there's enough that they're above the threshold, and they begin to rise. And however, at some point, the wolves eat too many of the deer, and then at that point, the population of the wolves gets high enough that it can no longer increase because there's not enough wolves to support, not enough deer to support more wolves. And then maybe you have the scenario where you keep importing wolves, and so you've got too many wolves, and then some of the wolves starve to death, and the population declines until you approach the limiting value. And so that encompasses all of the different possible scenarios. Okay, and that's 3 examples of how to go through and start off with an autonomous equation, use it to generate the phase line, and then once you have the phase line, take the phase line information, turn it into slopes, turn those slopes into a direction field, and then draw your curve onto the direction field. Okay, so if you've given an example where you're asked to go through and generate the graph of an autonomous equation, that's how you could do it. Now, whether it's a population related problem or not, you could just go through and given any autonomous equation, you could go through and generate equilibrium solutions, generate the phase line, use the phase line to generate the slopes, use the slopes to generate the direction field, and then the curves. Okay, so this video uses population dynamics, population models to go through and present the information for autonomous equations, but you couldn't go through and take the results and extend them and apply them to autonomous equations that are not population related. Okay, so thank you for watching. That's the video. Take care and have a good one.